then Pavel. Please do well to join us on stage. Please a round of applause for them. Thank you, thank you, thank you, thank you.
We have plenty of expertise here discussing benchmarking standards. We have, I guess, to the very end, we have Brett, the VP of product at RISC Zero. We have Ratan, which is the founding engineer at Succinct. And then we have Ismael, which is the co-founder and CEO of Lagrange. Plenty of expertise in the sector of ZK proving, and definitely want to hear your thoughts and perspectives on benchmarking standards. But before we dive deep into this topic, let's first give a round of introductions, what your project does, and how you're accelerating the ZK space. So starting with Brett.
I guess we'll start at this end. Hey everyone, I'm Brett Carter, VP of Product at RISC Zero. First started thinking about ZK benchmarking working for O1 Labs, the labs code behind MENA protocol. There's a former colleague right there. Yeah, so great to be here. Thanks for having me.
Let's see if I'll try this one first. Hello. I'm Ratan. I'm a founding engineer at Succinct. We've been working on SP1, which is a ZKVM which allows you to prove any RISC program. Most recently, I've been working on OP Succinct, which lets you prove any OP stack chain in ZK.
Thank you all for having me. My name is Ismael. I'm one of the co-founders of Lagrange Labs. We focus on two core things. The first being a ZK coprocessor that allows you to prove SQL-based computation over blockchain data. Think Dune Analytics, but verifiable on-chain. And the second being a decentralized prover network that powers our ZK coprocessor and other things for some of our friends.
Hello? I just got cut off. Hello?
You want my mic?
Sure, I guess we'll share. All right. Thank you for the introductions. I guess we'll get right into it in terms of the current state of benchmarking in the industry and where the primary challenges we face today in achieving fair and reproducible results. I guess we could start off with Ismael. Ismael, sorry.
I'll need my mic back for that. But so I think one of the difficulties in benchmarking standards is the decision of what the specifications of hardware and the equivalent comparison is across different systems. So we often talk about the difference between academic benchmarks and industry benchmarks. In an academic benchmark, what you want to do is find a normalized comparison between both systems. If system A can't do recursion, system B shouldn't be run in a recursive setup. If system A can't be parallelized, system B shouldn't be run in a parallel implementation. So you should compare them in a way that is agnostic in academia. In industry, the question is, for the performance of a use case, you should say the best running on system A versus the best run of system B, which one is more performant? Because that's the question that matters for a customer and end user. It's less of an intellectual pursuit and more of a practical one. And I think this is where we run into issues as an industry when doing benchmarking, because we either will take the approach of, I'm going to compare my best to your worst, or we take the approach of, we're going to limit the features of all of them and not have a comparison that's practical to end users.
Yeah, I think Ishmael brings up a great point, which is, I think I mostly agree here too, so I'm not sure if we're going to get much contention on this point, in that I think that industry benchmarks are really the thing we're optimizing for. Like, what do people care about? With ZK, it's two metrics, right? It's like cost and latency. And one really nice part about ZK is it's fully self-verifiable. So it doesn't matter where your compute gets done, it just matters that it gets done. And so as long as you're optimizing for benchmarks that output those two metrics, you have the things that you need. And I think in the early stages of ZK, it was interesting to take an academic approach. But I think as all of us here probably have noticed, what actually matters to the people that are using us is the fact that that cost is getting better by an order of magnitude year over year. The latency is getting progressively better in the systems too, and I think that is the right approach.
Yeah, what's interesting, lots of alignment here. There's a lot of things you could measure. You shouldn't necessarily measure all of them. I remember Delendum wrote a really nice sort of ZK benchmarking article maybe a year or two ago, and Remco Bloman did like a really great analysis of proof systems and their polynomial commitment performance. But in practice, those things don't matter too much, right? Like how that sort of gets to the end user, it's so far down and abstracted, those things aren't super useful today. So I think like application benchmarks, how fast can we prove an Ethereum block? What does that cost, et cetera? That's exactly where we want to be focused. What's interesting is like cost is actually something that's quite difficult to measure. And there's essentially no standard for. I think the closest we have to standard is like, hey, are you doing it on the same AWS instance as me? We're sort of using AWS and the fixed costs that are transparent and public to sort of measure cost, but that's something there's plenty of room to improve on as well.
And I think this is a good point too, which is like, I think until you reach a point where there's a market price, you're not going to get there. Yeah. And so I think right now, most of the proofs that are being generated are by the teams that made, the ZK VM or the ZK system. And when that changes to be a market system, then I think we'll have proper industry benchmarks, and that like there will no longer be a way to enforce, a different cost than the one you got, which is what the concern is with like, making sure people are running on the same AWS instance. Instead, the market will decide that, hey, I'm only willing to offer this service for this price, and that is what's going to give you the actual benchmark.
I mean, I think in many of these services, cost and latency are trade-offs. You can get lower latency by going more parallel on more expensive instances, and you can decrease cost by putting something on a single instance that's cheaper if it's not a GPU instance, and just run in sequence.
It's surprisingly not true in our proof system, because we can actually it's actually expensive to run it on a slow machine. Like for example, we could put it on a CPU instance that's quite inexpensive, but it does run much longer than it takes to sort of you don't get any actual cost savings in that case. You're right though in that having hundreds of machines available to generate a proof on does have an associated cost with it. And there's something that we called, like we've done pretty rigorous cost analysis on these things. There's something that we called, I actually can't remember the exact term, but essentially the downtime or like the latency, those machines not being active does have an associated cost. Once you have them though, like for example, you can keep up with all of mainnet Ethereum today for just a little bit more than 100 GPUs roughly. And so 100 GPUs aren't actually really that expensive, and so the downtime you're not using those machines also isn't that expensive. So the costs are just coming down so dramatically. I'm not sure that's quite as true as it was in a single machine instance or case as it is in a single machine instance or case.
Interesting, but you don't have any, but in theory, if you could go unbounded on how parallel you do your computation, you can do successfully larger proofs that you'd recursively combine. So I'd assume the statement that you could prove is fundamentally constrained by both cost and latency, which you can trade the two of those.
Yeah, it is. I guess so one of the important drivers here when it comes to performance is actually the speed at which you can execute today in a general purpose ZK VM. So for us, I don't quite know where Succinct is at right now, but on the average machine, it's like runs at about 30 megahertz. So we actually can't go unbounded is partly what I'm saying. We can go. We can only go up to like 100 machines, and you're bottlenecked at sort of that 100 machines right now.
Okay, that makes sense because you have a bound of 100 machines.
Yeah, exactly.
Okay,
roughly.
Right.
Yeah. And I should specify that's on an individual proof. If you could split up a proof, into multiple smaller proofs, you can also parallelize those 100, which so there is some aspect to which, there is a trade-off at some point. It's also an engineering complexity as well.
Yeah.
Yeah, I think I would agree here that cost and latency don't trade off as they do in normal systems, or as in previous ZK proof systems.
Or in computer science more broadly, right? Like if I was doing distributed computation of any type.
Sure, but the thing that's interesting here is like, okay, let's say you have 100 units of compute that you need to do. My point is, you can do 100, the parallelization cost is not that high. It's kind of my point. Like the cost that's induced by parallelism is much less than the units of compute. So like, kind of the point that you're making is, let's say we have 100 units of compute that we have to do. We're okay doing this on an instance that can do 1 unit of compute per timestamp. So like, let's say it does 1 unit of compute per second, but now you're saying in a parallelized system where let's say we want to do it in 1 second, you're going to induce a lot of units of compute additionally. My point is that additional induced cost is not that high. And so like what you see is that cost and latency don't trade off that much.
Interesting.
Yeah, I think the other assumption there is that like these computers are somewhat scarce, right? And in reality, like there's probably 100 people in this building that will give you access to hundreds or thousands of GPUs, and so we're at a certain place in immaturity in the market where supply significantly outweighs demand in terms of compute and for ZK proving.
Yeah. So it sounds like there's consensus and alignment in terms of the overall, like the cost and the latency for this. What about hardware requirements, like in terms of hardware standardizations? The talk about GPUs and these things, like should there be, and you said that if everyone's running on the same AWS machines, then essentially we are all in alignment. Like if one performs better on one type of machine versus another performing better on another type of machine, like should the machines themselves be standardized as part of this?
I think the better question to be asking is like, what is the purpose of benchmarking? It's like the purpose of benchmarking is to see how can we generate this proof as quickly as possible and as cheap as possible. And I think as we've mentioned, like the way that you actually verify the cost, to me at least long-term seems like the market cost. Like there will be some market for this in the future. There will be some associated costs that people are willing to offer this service at. And that's what's going to tell you how efficient that proof system is. Like, let's imagine that you can put any proof system on any hardware. With some amount of effort, you could do that. Now the question becomes, who's willing to offer this service? And that's what tells you, like, for Bitcoin, you have like the cost of hash rate, right? And like you can tell like who the most profitable miners are by where they're placing their Bitcoin miners around the world, and that tells you, okay, like this is the cost that I'm competing with. I think for proofs, you're going to see a similar dynamic. So I think it's interesting that we're in a transitory period from academic benchmarks into industry benchmarks. And so we're making these like weird trade-offs where we're like, no, like on GCP on this instance, it's better. No, on AWS of this instance, it's better. And like that clearly is directionally wrong. Like what we should care more about is like people are willing to offer the service for this price. That indicates what the price of doing this workload is on this specific proof system. Proof systems will have, they'll diverge in their costs for different workloads potentially. Maybe, one proof system will dominate on all workloads. Maybe there's a short time where like, let's say for example, one proof system is optimized for, specific kinds of operations more so, either, with like accelerators or precompiles. There will be divergence there. And so I think that's where you're going to see people are willing to offer the service at some cost. And that's what actually matters more so than like picking a specific instance. It's just like what cost you're getting quoted for proving a workload.
Yeah, I would agree. I think normalizing to the same instance for a bunch of very different proving backends is not the correct approach. I think what you want to do is say if you were to run proof system A within a certain cost constraint at the best possible speed you could run it, or a certain time constraint and the lowest possible cost you could run it, which would be better? And so I think, very generally, like that is what's relevant in the industry. I think the comparison to hash rate is very apt. And I also say, I think, the more benchmarks we're able to produce that kind of look at actual data of execution, for example, proving Ethereum, for example, proving the cost of a transfer, cost of a DEX swap, the better we'll be able to determine that which proof system is more relevant for certain applications in production.
Awesome. So I guess like the focus is on the real world. What the real world proof market, what people are paying for specific operations.
One point I'd like to make is I think we should send Fibonacci benchmarks to 0. Like those should not exist. Like why? Like I've heard multiple people ask me like, oh my God, like this proof system is better on Fibonacci. I'm like,
which is like cute when you can only write a circuit to do Fibonacci, right? But in a general purpose ZKVM, which has much more utility than that, they're pretty useless.
Like I think the bar for what you are benchmarking on goes up over time, right? And I think we're at a point where we should stop as an industry like benchmarking on things that don't matter and benchmark on things that do.
And in terms of the things that do matter, in terms of what the direction. So I know that the OP Succinct, like you're directly working on that aspect. Are there any other types of benchmarking that would be I would say like where do you see more of that being used as relevant metrics and statistics for that?
Yeah, I mean Ismael can feel free to jump in.
No, the question's to you. You jump in first.
I think rollups are a clear use case. I think that OP-Stack is one of many. There are many different rollups that have many different configurations, right? Teams roll their own rollup stacks. And I think that for benchmarking, it's probably good to have consolidation around, one specific kind of rollup stack, or you can maybe test the common ones. But then what's interesting is like people are also going to test for their own rollup stacks what the performance is. So I think rollups are a clear one. I think bridging is another use case where it's like you have some recurring proof that's being posted in order to migrate the state over. I think in applications that kind of have this recurring nature, benchmarking on the real cost and latency matters a lot. And so I think other applications that fall in that category probably would be things that I'd benchmark. So rollups and bridges are clear.
Proof recursion is probably a good third category that's emerging.
Yeah,
Like
I think
the cost of maintaining proofs from disparate proof systems and aggregating those in an individual proof.
Fully agree with that. I would also, as a counterpoint, I would think that we need to be more specific on what is actually being benchmarked when benchmarking roll-up execution, because it's a very different cost to prove a transaction versus swap versus a precompile. And I think it's, we talk about, oh, you can prove a transfer in a fraction of a cent, but that doesn't really give the full picture of how much it would cost to run a ZK rollup within a ZK VM for a material period of time. And I think that's part of the issue that we still face with our benchmarking, because these are still not practical when we are looking at very specific types of transactions that might not be reflected at the correct scale in actual live execution environments. So I think a much more relevant benchmark is, for example, proving Ethereum block execution, which has a very large heterogeneity of what the transactions, in fact, that are included in that.
Yeah, what's funny about that is there's still quite a bit of variety in the size of blocks, for example, right?
It is,
so,
but like over a duration.
Sure, yeah. Like I think mainnet is actually a good standard, right? Like some sampling of mainnet blocks, having an average gas size, of et cetera. Because I've actually realized in some of, we talk about Ethereum block proving, well, most OP blocks are empty, for example. So you can prove those for a lot less expensive, to prove an OP mainnet block on average than it is to prove an Ethereum block. You also have difference in block frequency, right? So like the operational cost of running a rollup itself can vary because of those parameters.
Yeah, I think just prove the chain and you'll know how much it costs. Yeah, I think that's the right metric for rollup benchmarking is like, this is what we see with OP Succinct is like, you can take any OP stack chain and prove it. And like, we can determine the cost for that, like very concretely. And in a world where, many different provers, then you have like a market cost for that as well. And that gives you your benchmark. And
so could you determine that a priori to them working with you, or would you have to go through and prove the whole thing to tell them how much it costs?
You have rough metrics that have like, it depends on what hardware you're running it on, right? Like for example, pricing is difficult because let's say we even isolate it to cloud. Like people have reserve deals. Some people might be using a home data center that has different costs. So cost is difficult for you to assess a priority without knowing what the cost of compute is for an external party. Like for example, let's say you have a bunch of compute. I can't tell you how much it's gonna cost for you to run it. Only you can tell that. But you can see before you run it, okay, let's say you've been running an hour of, OP mainnet blocks or Ethereum blocks. You now have a good gauge of how your execution of that block maps to the actual proving cost. So you can execute it for a fraction of the time that it takes to prove it. And it's quite a cheap operation, and then you can use some regression analysis to determine, okay, given this new block, here's what it's going to cost me to run it. So I think there are actually quite good metrics that you can get from seeing how your workload performance on your own whatever compute that you have, and then determine your costs. But it's compute provider specific.
That's interesting, because that's a comment on the lack of the value of benchmarks prior to a customer directly engaging with each of the teams. Because if you require them, but that's a very interesting point, because that's kind of against a lot of the early topics we're discussing on the panel about having industry-wide benchmarks. This is a comment for not having industry-wide benchmarks. It's a comment for saying we shouldn't benchmark anything. We should instead just directly engage with counterparties and have them test each system and see which one is more performant for their workload.
I think to Pavel's point, it's more a comment about the lack of an open market for proofs. That when there is an open market, a transparent market for buying proofs for various chains, it'll be a lot easier to have these standards, and we're just lacking that today.
Got it. So in terms of the overall what the discussion is proving based on the real world application. What the real world application is proving Ethereum blocks, and in that way, we can of course. Design our own proof systems to be highly optimized for that specific use case, but then having it being with an open prover marketplace, you can essentially see how it works in the real world on various different types of machines, and how those machines can then generate proofs efficiently based on the variety
Yeah.
of these
Yeah.
things.
I'll say too, I think like the closest thing we have to that right now, and maybe this will give like Pavel a laugh, is like when you have a team that's working with the ZKVM, the best way to figure out what the cost to prove your given payload is to just like port the SP1 guess into RISC-0 or vice versa, and then ask them what the cost is, you know, and that's really the most practical sort of assessment you can do in terms of cost right now. You know, eventually, you know, as we have these open markets, and actually, I would like to ask Ismael to some extent. We're sort of hogging the agenda, mostly talking about block proving and stuff. How should we be thinking about cost versus latency and sort of like historical proofs on chain as well? How are you guys thinking about the cost drivers for those?
Yeah, that's a really good point. So for us, it really comes down to how many data elements are touched in a given proof, as well as fixed costs on pre-processing of data. So the way we do our proving is really in two steps. We have a pre-processing phase where we use an updatable vector commitment that our team published a paper on recently called RECL trees to generate a batch proof of the inclusion of a large subset of data within a given blockchain, either receipts, transactions, storage. And whenever a new block gets in, we update that vector commitment to include the new data. And what we prove with this inclusion proof is both the existence of some subset of elements within the tree and the equivalence of the data contained within the tree to a new data structure that's more performant to compute proofs over. We remove the RLP encodings, we remove the catch-back hash, and we change the arity of the tree. And then so we, have, in essence, have a giant binary Merkle tree built with Poseidon 2 that's much more performant to generate proofs over top of it. We can change it to an algebraic hash if we want. In the future, there's nothing that constrains us there. And then we can compute very, very large queries over this new optimized structure because we no longer have to deal with what is a very large unbalanced tree of a varying arity, which is the MPT tree with obviously block connection. And so because of that, we can go very far back in queries or over a very large range of blocks in queries in a much more performant way. And so for us, cost drivers are two things. It's how much does it cost to generate that pre-processing for the contracts that we need to generate proofs over, then how much does it cost to generate an arbitrary query over that data when requested. Generating the arbitrary query is actually very cheap, and it amortizes the pre-processing cost across it. So it's very much like a volume-based pricing model, the same way you'd expect in a lot of software. If you need to make a very small number of queries to a data set that's very large, and you need to store that data set, it's expensive. If you need to make frequent queries to a very large data set, it's on a per query basis much cheaper.
It's interesting because just a realization just now that's maybe useful to externalize and say is, when we're looking at the cost of proving a chain, you sort of have two different paradigms. You have optimistic rollups, you have validity rollups. And in a validity rollup, the proving cost is incremental to the operational cost of the optimistic rollup, right? It's an additional cost if you think about it on the balance sheet. When you're using a coprocessor, you're actually not like sort of competing with another prover. You're actually competing with on-chain execution, right? So that's actually, I think it's useful to actually look at, and I'd be curious to know in Lagrange's case, like the amount of compute you were able to offset from the chain itself and how those costs sort of compare.
So it's not just compute, it's storage. Because if you want historical data available at the current state of the chain, you have to store that. Yeah. And every storage read is I think
3,000 gas, right, for S storage or S load?
Yeah, right. S load is right. Yeah. But read is about 2,100. And so you can think of if you need to structure a very large computation over some large subset of storage. Let's say you want 1 million events that you're going to store in a mapping. Every time someone does something, instead of emitting an event, you're going to store it in a mapping. Well, you can think of the cost of that relatively high, over 1 billion gas or 3 billion gas. And then to read on that, every query you're going to have to do is going to be proportionally high as well. So, I mean, even structuring a very basic query like select all NFTs that you own between block X and X plus K would be infeasible to write in Solidity. Especially when the number of blocks you're querying over K is very, very large. And so in our current benchmarks, we can handle queries of about over 1 million storage slots in sub 1 minute over an arbitrary block range. And that, we think is an order of magnitude greater functionality available to dApp developers than what they can do right now in Solidity.
I have an implementation question that might be a little bit nitty gritty. Do you guys walk back in the consensus tree to get the store? You get the
go back and epoch at a time. And
you go back and epoch at a time. You open and then you.
The whole thing unfurls. You can think of the blockchain as a very large unbalanced binary tree, right? All the blocks are connected with RLP encoding and catch-back hashes, and every tree is connected that way too. So if you're structuring a batch proof, you have to structure the batch proof over this like very large unbalanced tree. Then a new block is added, and you have to update the underlying batch proof to be verifiable with respect to the most recent block header. So the public input to the proof is just whatever the most recent block header is of the chain, and you can go arbitrarily deep. And when you're recomputing, because we've changed the arity of the structure, you don't have to compute a number of hashes proportionate to length.
Like, bringing it back, and I guess like the last question in terms of the panel, what are the biggest opportunity for improving the benchmarking practices? Like I know we have different focuses here in terms of optimizing, in terms of doing these things, and I know that there's that look at the market demand, look at the different like the block spaces, as well as like essentially what can we do in order to achieve like that set standard, other than just following what the market is saying?
Build, baby, build. Build something useful, build something people want to use, and then benchmark it on real world use cases with technology that's in production. That's what you have to do.
I think we need a market, right? I mean, that's like a clear conclusion from this. We need an open, permissionless market where these, the prices for these things are transparent. That's something I guess I could chill. We're building a protocol called Boundless to do exactly that, sort of open up the proof supply chain, if you will, fully decentralized manner. I believe the Succinct team's working on something similar, and so that to me is like one of the most important things we need to solve in order to make this not only the benchmarks themselves more transparent, but in order to make this technology feasible and scalable, et cetera.
Yeah, I think too, it's interesting to know there's so much agreement, across the board, because I think that benchmarks are quite splashy. I'm glad that we're moving to an era where it's like focused on real workloads. And I think that, it'll be really interesting to see how the kinds of workloads that we do change. I think, at least to me, it's pretty clear that a lot of the rollup demand, I think, will move into ZK rollups. And once that happens, the next workloads for benchmarking get much more interesting. Like with ZK rollups, you have these like large workloads that are done by chains. What happens when your workloads are done by consumers, right? Like what happens when you have like millions of incredibly heavy client-side proofs or just like consumer proofs that are happening, and what does it actually look like to optimize for that regime and have like benchmarks that work well for people? Because let's say you're running a protocol that is incurring those costs on consumers, the way you think about your pricing model is very different than you have to think about it with a rollup, right? Like with a rollup, all of the costs are done by the service provider. When you're pushing those costs into the consumers, how do you think about that? And how do you think about, subsidizing that as an application? I think that's gonna be quite cool. And I think at Succinct is also a big priority for us to make sure that getting this market rate mechanism is incredibly important. Getting it right is important. There are many ways to price things, but some of them are better at accruing value to the end users of, let's say, a prover network. And to us, it's very clear that that needs to be done critically well and with a lot of thought about making sure that the excess value is pushed to applications and not towards the market.
To interject very quickly, so our team also focused on building prover markets, prover networks, and underlying infrastructure to do decentralized proving. And one thing that was very relevant for us is research into mechanism design and informal proofs around mechanism design for resource allocation and resource markets. And so we have a great paper our team actually just came out with called DARA, or Double Auctions for Resource Allocation, which is, to my knowledge, the first incentive-compatible design for proof assignment in a double-sided marketplace for proof demand. And so I suggest anyone here who's interested in that, definitely go check it out. It's, I think, some really good work. It's submitted to Financial Cryptography this year, and it's exciting.
Awesome. And I think we're on time with this. Thank you all for sharing your thoughts, and glad to see alignment.
Yeah, thank you.
Thank you, everyone.
Thank you.
Thank you for having us.